Howdy, folks. My name's Danny, and I'm here to present the Y Lab session for the IA Monitoring Summit. Today, we're going to be talking about monitoring on structured data and beyond. And as if that wasn't enough of a mouthful already, I decided to add a subtitle to try to clarify what we're going to be discussing today. We're going to be giving you a hands-on monitoring and observability for tabular, image/computer vision, text, and natural language processing data, and more presentation. So that's a lot of information to try to pack into a single hour. We might speak a little bit quickly, but hopefully we'll be able to cram in all of the really exciting information and content that we've got prepared for you today. Before we launch into that content, I wanted to introduce the three speakers that we've got here. I figured, if there's a full hour, you guys are probably going to get bored of hearing the sound of my voice. So I wanted to bring along some of my esteemed colleagues. My name's Danny, and I'm an MLOps architect, but we've also got Bernice, a senior data scientist who's going to be speaking, and Ray, who's a customer success data scientist. And we're all going to be speaking on different subjects today, all around the themes of monitoring, observability, and unstructured data. I'm going to start us off with a conversation about Y logs and Y labs and kind of making the differentiation there. That's going to be really pivotal to understand, to understand how it is that we deal with structured and unstructured data. Then I'm going to hand the mic over to Bernice so that she can talk about Y logs and really dive into how Y logs and Y labs handle unstructured data. Then Bernice will hand it over to Ray so that he can talk about image data for computer vision. And then Bernice will wrap us up with some monitoring text data for NLP example. And then I'm going to give a very brief conclusion. So with this agenda in mind, let's do a quick intro about Y logs and Y labs. This is a really important thing to understand before diving into the specific of unstructured data. So when Y labs was founded, the founders realized that there was kind of a gap in the market in both data and machine learning in the way that companies could monitor, observe, and generally establish the reliability of their machine learning and data systems. So if you think about like classic software 1.0 engineering, you can build applications with code on whatever kind of IDE you want. You can run them with Docker or Kubernetes, Lambda functions, EC2, and there's all of this functionality and all of this tooling out there, StatsD, all of these different monitoring metric agents, and all of these different libraries, as well as SaaS offerings like Splunk or Grafana and Prometheus or New Relic that allow you to monitor these kinds of software 1.0 applications, this application performance monitoring. But what we realized was that there was a big gap in the market because although there was all of this great tooling in place for software 1.0, there was really a big gap for what might be referred to by Andrew Karpathy as software 2.0, right? For machine learning and database systems, although there is, an absolute explosion in the tooling possibilities for building machine learning models, for running and deploying machine learning models, there's really a big gap for being able to log data from those models in order to be able to monitor them in production. And, I know it's the end of the day, so I'm not going to bore you guys with too much detail about why monitoring and observability are so important from machine learning models. I'm sure that you've heard this from all of the other great speakers in today's sessions, but just to reiterate, in order to understand how your model is performing, in order to ensure that it's performing in production well, you need to be able to monitor it. And in order to fix problems that might occur in your machine learning system, you need to have observability across the system as a whole. So with this in mind, and kind of taking a look over the shoulders of our neighbors in the DevOps world, we developed Y logs as a logging agent and Y labs as a SaaS platform. So let's kind of dive into this approach, which is pretty unique in the MLOps world, but actually very standard in the DevOps world. So we've got a production environment, and this can mean different things at different companies, right? You could have live inference with real-time data coming in and predictions being served in real time. You can have batch inference where on a regular cadence, like every day or every week or every month, you're generating predictions. You've got your training and your testing environment. You've got a feature store. You've got all of these different things where basically models, the data that get fed to them, all of these different components of your ML system live. And then in order to be able to monitor that production environment, you need to have some kind of telemetry application, this AI telemetry square in this chart. Then what that telemetry does is it allows you to bridge the gap between the production environment and the observability system you have, some kind of AI observability platform that gives you like an anomaly detection engine to tell you when something's wrong, that gives you a debugging engine so that you can understand what's wrong and solve it, that can be used by your data scientists, your machine learning engineers, and can even trigger ML pipelines to retrain models or roll back data pipelines to previous versions. So this high level approach is really key to understanding our approach to monitoring both structured as well as unstructured data. So let's dive into the particular tools and technologies that we use to build this architecture and this framework. The first one is YLogs. YLogs is the open standard for data logging. It basically, what it does is it takes in data, and that can be tabular data, Spark data frames, Pandas data frames, Python dictionaries, whatever it might be, or images or text, as Bernice and Ray are going to be talking about. And it outputs statistical summaries of that data. And what these summaries do is they represent that data in a way that's efficient. So it stores a lot of information about your data set in a really small package, customizable so that you can add more features that you want to track about your data. And Bernice and Ray are going to talk more about this in their sessions, as well as mergeable, which means that it can work on streaming data, it can work in distributed systems, it can work across a whole number of different applications. So just the important thing to keep in mind about YLogs, it's an open source library. You can check us out on GitHub, and all it does is it takes in data and it produces data profiles. Now, these data profiles, these statistical summaries of data, can be used for a number of different things. They can be visualized with the profile visualizer that we've got built into YLogs. They can be set constraints on with the constraints feature that we have in YLogs, which you can basically use to do data quality validation if you've got expectations about how you think your data should look. And one of the applications of YLogs is that they can be sent to the YLabs AI Observatory. So the YLabs AI Observatory is a fully software as a service platform, which means that it runs entirely on our hardware. You never have to think about scaling up your infrastructure or managing it in any way. It's entirely managed by us. And what it does is it gives you this observability store where you take in these logs, as we've been talking about these YLogs profiles, you store them, you aggregate them, and from that, you can do forecasting and querying, you can detect potential problems. Overall, you can monitor your machine learning models. And importantly, this observability store has three actions associated, or three types of actions associated with it. One is reports and dashboards, just visualizations of the data, of the profiles that are being stored in the observability store. This is really useful for observability, for debugging problems that might be occurring with your machine learning system. It also enables alerts and notifications so that if there is a problem, a data scientist or machine learning engineer knows to go back to those reports and dashboards. And finally, it also enables triggers and workflows, automation around the pipeline, around the ML system, which enable you to automatically fix problems as they're occurring with your ML system. So that's kind of the breakdown of YLogs and YLabs. This is something that trips people up quite a bit, and I think it's really important to emphasize it early on because it's really key to understanding how YLabs as a SaaS platform can be used for monitoring both image data, text data, as well as structured data. So with that, I'm gonna release the mic and give it over to Bernice to dive more into how we deal with unstructured data.
Hi, so I'm Bernice. I'm going to talk more about monitoring structured and unstructured data. So we really need to talk a bit about structured to get to unstructured. And the first question is, what is structured versus unstructured data? There's different interpretations of these two terms. I really enjoy talking about kind of the various usage of this term and how this has evolved. But I'll focus on the most common definitions that we see in the databases community, machine learning communities, and data science communities. So structured data, we often refer to as tabular data. You might see it in the form of CSVs or relational databases and other places. This idea really came out of the database community with relational databases, with COD. And this often is a number of rows and columns with fairly simple data types comprising those columns and rows. So things like numbers or short amounts of text, just a small set of data types. You're quite familiar with these, I imagine. Unstructured data kind of takes the rest, and what we often mean by that are things like images and text and embeddings, many other different data types, audio, things like that. And these present some complexity, but in the same way also present some really interesting homogeny within it. So we'll refer mostly to the complexity, and the things that are really important to think about is that unstructured data, although it doesn't have to be this case, unstructured data often is harder to interpret, especially in aggregate, and we'll talk more about that. But there's a lot of strategies that you have to consider to both deal with the file type and interpret the data at times. Okay, so let's talk about monitoring. How do you monitor data and machine learning models generally so we can get to thinking about unstructured data specifically? Okay, so I would posit that there are two key ingredients to monitoring data or machine learning models, either one. One is collecting insights from the data. So summarizing information about the massive amount of data you likely have into a useful and digestible form. Without that, you can't provide insights or kind of specific things to monitor. What you're providing is access to data, which can be great in some ways, but not what we're normally talking about. And the second is alerting the stakeholders or users. So while you may have some way to summarize information, presenting that on its own is not quite enough because there's lots of information even after summarizing. And what you often want to do is detect interesting or alarming data to which users should pay attention. And both of these will change a bit when we're going from structured data to unstructured data. But we want to really focus on number one in this presentation. While there's some differences in the algorithms and visualizations you may use to alert and determine which data points to surface to users for structured data versus unstructured, I'm really going to focus on the gathering insights because that tends to have a lot more difference between these two types of data. Okay, so capturing scalar metrics for data and machine learning models. This is often the process that people go through to capture insights from large amounts of data. And this may happen in different locations in your pipeline. So for example, us at Y Labs, we have this, this inside of our open source Y Logs project, but other people may do this other places. You may download all the data somewhere and then capture these metrics at a different time. These are, so what I'm focusing on here are scalar metrics. So these are things that result in kind of a single number. So, and you'll see these lots of places. So means, standard deviations, quantiles, if you're able to capture them, many other metrics you may capture. And then there may be performance specific metrics. So the first half were kind of specific to the data. And the second half, performance metrics, may be specific to the model and data. So things like accuracy, precision, recall, these sorts of things. And there's some thought that has to go into this about how many dimensions you have of the data. So you'll see here, this is likely representing univariate distribution. So one dimension of your data. And so what this might mean is that for structured data, this is just one feature or one column of your data. But these scalar metrics, even if you collect them for each of the columns, isn't really enough to root cause a production system. Gathering insights with these scalar metrics alone prevents a number of questions to be answered at your organization, all of them quite important. So things like, what would a new metric X be on historical data? So if you've collected these metrics in the past, and then you've determined that now I want to add this additional quantile or start collecting some different measure of spread. How would you start to collect that on the past data? This can be really difficult when you use scalar metrics, depending on your data retention strategy. And scalar metrics alone just won't get it done. What are the metrics in the last 6 months of your data combined? So this is a problem that people run into very often, which is I decide to collect these scalar metrics, maybe per day, maybe on some cadence. But then at some point, I want to aggregate these together. I want to consider a larger amount of data or a smaller amount of data, a smaller amount of time. And this is virtually impossible with scalar metrics without taking a lot of care for capturing intermediate values and a lot of work that frankly does not apply for all of the metrics. You won't be able to do. What are the metrics across my distributed systems? So very similar to the one before. If you have your model across multiple machines, I don't just want metrics for that one machine, or I might want that, but I also want metrics for my system as a whole. And so being able to look at these and combine these is very important. And then there's lots of other questions that are deep in your analysis of trying to resolve a problem. So for example, how many unique values are estimated to overlap between these two data sets? Maybe I have some measure of how many unique values I've seen, but what I would need to know is when I combine these two together, or when I compare these two, how many of them overlap? How many of them are in common? Things like error bounds on these calculations. So whenever you have any estimates for these metrics, which you may have when you combine or may have individually, you need to understand kind of what are the error bounds and limitations of that point estimate you've given. And then finally, will our existing system adopt to online and streaming loads? So there are many cases for production models where you're either doing this work online, which means I am taking in data likely in a streaming form, and at any time I can give kind of information or a prediction from my model, or you're doing it streaming where you're taking in the data and not necessarily giving the predictions at any instance. But either way, these are very popular and growing use cases. And so making sure that your approach matches this is very important. So these complex data structures that go beyond the scalar metrics are what are going to be key here. So that, along with mergeability, I've mentioned in several cases where you'll have some amount of data and you'll have some other data, maybe for another time or another system, and you want to be able to combine those intelligently. And that's really difficult to do with scalar. So this is why we came up with ylogs and why we use Apache data sketches, and the entire field of data sketching is a strongly supported academic area, lots of rigorous research. And there's a lot of great properties that are really necessary to do production, machine learning, observability, and monitoring correctly. So efficiency, customizability, mergeability, Danny mentioned, but being statistically sound, having those error bars, working for online and streaming data. Okay, now let's get to gathering insights from structured data. So structured data, we'll use this kind of CSV example again, is easily aggregated, often by column. A little harder to aggregate across columns at times. So here on the left is just an example of a couple of rows of some data. And common aggregations that you may see for numerical values are metrics like mean and median, standard deviation, interquartile range, these sorts of things. Categorical values may be like the most frequent item, maybe a histogram, uniqueness. And then there are other types, so things like dates, you may collect by grouping by year or month or day of week, or you may convert to some other data type like numerical values using seconds since 1970. It's a very common one. Okay. And I think the key thing to think about when we're comparing structured data to unstructured data is that aggregate structured data is well understood. We're fairly used to this. You may have many millions or billions of rows of columns, And we're comfortable dealing with the mean of a distribution, the standard deviation, and reasoning about these, especially with the aid of things like quantile, particular quantiles to get something that looks like a histogram. And so for structured data, these are just a partial list of the sorts of metrics and data sketches and Y logs that we use to capture structured data. And we're going to contrast this with unstructured data in a second. So things like counts, types, ints, distributional information, cardinality, so unique values, frequent items. And there's a number of sketches that we use inside of Y logs. Okay, so now let's get to unstructured data, the really juicy part. So the question is what kind of data structures and metrics are we going to collect for unstructured data? And unstructured data, the first thing to note is that unstructured data is rarely just this raw unstructured data. It's often paired with metadata about your data system and environment. So all that we just talked about for structured data is going to apply in lots of these cases because we want to be able to capture that structured data as well as the image or text or other things that you're capturing. And then the second thing to note is that histograms and other complex data structures are used more broadly across these kind of unstructured data types. So images and text and these other complex data types require more advanced data structures. Scalar values are really helpful and provide a number of benefits, and we'll see many of those. But this will require histograms and even more complex data structures that I'll talk about in a second, even further. So yes, let's go into that. So one thing I want to note, I mentioned histograms, and sometimes people say, oh, histograms, that's not that complex. But histograms really do back a lot of features that we think about for unstructured data, some more classic and some even modern. So the example I have here are hog features. So these are the histogram of gradients, and you use this in images. It was a kind of a classic feature that you used in computer vision. And so what you would do here is you would take your image, you would do some sort of edge detection on it, and you would gather gradients across the image. And you would take those gradients and you would bin them, and you would create a histogram of those gradient bins. And this is very, very informative. You can use this to classify images, and people did all of the time. And then we've gotten more complex things. And histograms of information still is very, very present today. So one analogy to this that is very new and that is used in computer vision and quite successful these days, these are the variants of gradients. So the work here, I didn't show this in a histogram, but the work here is instead of just looking at a single image and doing image edge detection, what we're going to do instead is we're going to look at the deep learning model that we built for that we trained, and we are going to look across the training time at the different gradients that we have over time. And the variance of those gradients tells you a lot of information about this image, particularly things like the difficulty of the image. So it's the image related to the model. So things like the difficulty of the image, lots of other information about the image. And then switching over to text on the right, we have something like unigram frequency or any other of texts or tokens and things like this. Seeing frequency of unigrams or texts or tokens can be really helpful in understanding text. It was a very, very often used technique and still is. Now I'm going to quickly just discuss some more advanced techniques that sketching allows us to do for high dimensional data under which unstructured data often falls. So one is locality sensitive hashing. This is a technique, if you've ever seen approximate nearest neighbors algorithms or algorithms to compare images or things like that very quickly, they often use locality sensitive hashing. I mean, I won't go into the algorithm at all, but I'm happy to discuss more about this later. But this is a technique that can be embedded in a sketch. This is not something that you can do. It's really difficult to do high dimensional data elsewhere outside of the sketching technique that we provide in YLogs. Another example is singular value decomposition. So if you are familiar or remember PCA, SVD is kind of the backbone of PCA, principal components analysis, and that's what allows us to reduce dimensionality of our data. And this is also something that is implemented in data sketches, and we have available to us in YLogs for sketching. And these are the tools that allow us to work on unstructured data. So I wanted to quickly go through the metrics and sketches that you need for unstructured data in a view that's kind of similar to what we saw for the structured. So for images, we have things like hue, saturation, brightness, EXIF data, color histograms, histograms of gradients, many others. And Ray's going to talk about those. We have text. So the number and distributions of the tokens that you have, or words, the lengths of your strings, the Unicode character presence, and many others. All of these are inside of YLogs. Geospatial data. So if you're creating now insights for geospatial data, you will collect things like latitude and longitude, but then start to add more complex metrics, things like driving distance as opposed to just street distance, things like census tracts and other demographic information is very common here. Vectorization of your data and more that we hope to include and introduce in the future. And then for the last example I'll give here is embeddings. And so there are sparse embeddings or vectors of data that you have, maybe a bag of words for your text. There are dense embeddings. So we build embeddings for lots of things, images, text, documents, all sorts of stuff. And these also are have with them a number of metrics that you can collect and use. So then I want to talk about the sketches that we'll use. So all of the structured data sketches apply because a number of these metrics that we collect are now numerical metrics. And we want to do the same histograms and cardinality counts and sorts of things on those data points as we've done for the structured data. But in addition to that, we have things like sketches that allow us to do conditional histograms. So based on a particular kind of area of the graph, I may want to condition on some relation and only see the histogram for that. This is really important for unstructured data. Things like frequent directions data sketch. So this is the single value decomposition. Things like LSH hashing. Locality sensitive hashing. This is also important. Okay. And I want to finish up here by talking about how our work on YLogs to make performance, improve customizability is really, really crucial for unstructured data because unstructured data has just inherently more calculation, more crunching of data, and we've made some massive performance improvements in our very recent launch of YLogs v1. So you can see up to 500x performance improvements here. And this really is what enables us at YLabs to do unstructured data monitoring in a way that others who don't have these sketch-based techniques and don't have them as efficient as we've done will struggle to do. All right. And that is all I want to share about unstructured data at the high level. I'm going to pass it on to Ray, our customer success data scientist, to talk in detail about image data and a demo for that.
Thank you, Bernice. So as Bernice mentioned, I'm Ray. I'm going to be diving into the case of monitoring image data a bit more deeply. So as we saw with structured data, we can easily monitor simple telemetry, like you see in the list here. But when we think about monitoring the structured data on a feature by feature level, this doesn't really work for images. We usually think of, in computer vision cases, we usually think of images as each pixel being a feature, which means we have hundreds of thousands to millions of features. A particular pixel in one image has no relation to the same pixel in another image. And we might not even have the same number of features from image to image. So we need a very different approach than what we do for structured data for images. And before, of course, it's a computer vision demo, so we're going to see dogs and or cats. But before we talk about what metrics specifically we want to monitor and why we choose to monitor them, we have to start with the problem. We have to start with what are the common challenges that we typically run into when doing computer vision. And these are typically things like we could have images of different sizes. Depending on your use case, you could have images coming from a wide variety of different hardware, producing images with different resolution, different image quality, and even external factors can impact image quality in those cases. Brightness can vary from one set of images to the next. If you consider a simple case where you have a computer vision system doing inspection on an assembly line and somebody changes the light bulbs in the factory, that can suddenly impact your model in a way that impacts its performance just by that slight change of brightness. For object size, like this dog in the lower right-hand corner, if we have big differences in the size of an object that we're doing object detection on, that could impact our models, because a convolutional neural network is not impacted by where a specific object is in an image, but it is sensitive to the size of that object within an image. Things like the number of objects. We have more or less objects in a typical image of our production data versus our training data. That could negatively impact our models. And of course, something like inconsistent backgrounds. An obvious case is if we have images coming through production with very different backgrounds than the background seen in training images, that could be a problem. But also this could we could have some kind of pre-processing being done that is sensitive to the backgrounds in our images, especially if we're doing some kind of background removal. So even if all the images that are being fed to our model, even if all those images are representative of our training data, they fall within the parameters our model have been trained on, we still run into some big issues because we typically touch these images before they're being fed to models. We usually manipulate them or pre-process them in some way. And a couple of the things that we might run into are, suppose we decided to switch to a different image processing tool, which reads in images in a slightly different way. That might result in color channels being swapped. And we might get something like this blue dog we see here. We could have a case where we're dealing with both color images and grayscale images. That ratio could be changing over time. One particularly damaging effect is if we introduce some kind of bug in the way that we're scaling images. So some image processing libraries might use values from 0 to 255 for pixel values. Some might use 0 to 1. If we make some kind of mistake in our pre-processing, we could end up with a dog that looks like this, which is a real shame because this was actually the cutest dog in all of the examples that I had. As one more example, we could have the shape of the post-processed images changing as well. Okay, so it's a lot of these things are not only important to get a handle on before our images even go through our pre-processing, but after our pre-processing as well. So how can we monitor this? There are a few approaches. As was mentioned earlier, we could look for metadata that's tied to this unstructured data. And EXIF data is an example of exactly this. So EXIF data is typically, you can think of it as structured data that describes certain conditions surrounding the image that was taken. Any photographer will tell you that the three most important parameters to tune on their cameras are the ISO, aperture, and shutter speed. And things like this are tracked in EXIF data in most cases. And these things do have real impacts on the images, which a model could be sensitive to. So EXIF data gives us a start, but this is only scratching the surface of the types of metrics we could be interested in, which could impact our when it comes to image data. So another approach that we could take is calculating metrics that we're interested in from the image itself. We could easily calculate brightness by taking the average of pixel values across our image and computing that for each image in our data set. We could look at the standard deviation of that brightness, which will give us some indication of sharpness of the image. We can convert our image to the HSV color space and gather information about the hue and saturation. And in the HSV color space, it actually separates the color information about an image from the intensity information about an image. So hue and saturation will contain valuable and intuitive information about the color palette within the images in our data set. Again, we could directly calculate the image height and width, and even other metrics such as sharpness, such as noise levels. We can calculate any of these additional more advanced metrics and include these depending on what is useful for our particular data set. So there's another thing that we could do as well. Instead of just looking at the images themselves, we could look at the model outputs that we're feeding these images into. In the case of object detection, we could look at the bounding boxes that our model generates. We could look at the count for how many objects we have, and we could look at the area of the bounding boxes as well, which represents how big our image or object is within our image. That could be done for both the model output as well as the ground truths if we have them. A bit more of an advanced technique is we could look at the actual layer outputs. If we're using a convolutional neural network, we could look at, for instance, the output of the first convolutional layer, as well as the last fully connected layer. And through the approaches that Bernice discussed, we could actually monitor the outputs of these layers directly. If we have predictions and actuals, we could track any kind of performance metrics that we want to track about the model. We could see when our model begins to suffer. And in addition to that, we could track all kinds of metadata about the data pipeline itself in the ecosystem. So we can pair this image data with things like the versions of the libraries we're using, model versions, the most recent deployment to any kind of pipeline update or anything like that, which could help us tie any anomalies to changes that we did on our end, and help us if it's us or if it's the data that is at fault. So our open source library YLogs is designed to log a lot of these metrics we're interested in right out of the box. So things like brightness, saturation, hue. We make it very easy for users to introduce custom functions if they want to compute values that aren't available out of the box. They can make this advanced and comprehensive as they wish. If EXIF data is tied to these images, this EXIF data will be included along with the profile, and users can also log data for supplemental metadata about the pipeline, or in the case of multimodal models, users can log text data that's associated with these images, or structured data, or any other type of data that is paired with these images we're working with. So in this quick example, I'm going to walk through a case where YLogs is used to profile two sets of images. We have three examples here just to show you what a baseline looks like. And some of our images in our production set, it looks like the color's a bit off in these. We might have some channels being swapped. And in this other set here, we have some images which appear quite a bit darker than others. So the first thing I do here is I'm going to start a session, and I'm looping over each of my images and profiling each image. And I also have a supplemental data set containing some metadata about the environment and about the camera itself, which could be important for this case. So I log each of these. I could generate a summary of the profile that's been generated from profiling this set of images. I could see things like the saturation, the mean, min, max, some basic descriptive statistics about the distribution of those metrics. And I also see things like the shutter speed, which is captured for these images as well. I'm going to repeat this process for the test images that we have in production. And YLogs has a variety of visualization tools available. One of these is a browser-based one, which I'm going to jump into just to show what these profiles look like when we generate them. So as Bernice mentioned, it's important to not just capture these scalar metrics, but we also capture these distributions. So of these 50 images, we could see what the distribution of the mean saturation is for each image, and see how this changes from our reference data set, which was used for training, versus the new data we see coming into production. So in practice, ideally, what we'd want to do with these profiles, if we want to set up a robust monitoring solution, we'd want a way to take these profiles and collect them over time. So maybe each day I could profile all of the images that flowed through my pipeline for that day, profile that set of images, and I'd really like a way to apply automatic anomaly detection to those profiles. I'd really like a way to dig into these profiles when an anomaly occurs, to do some root cause analysis and dig further to see what's going on. And I'd really like a way to get notified automatically through common communication channels like Slack and email. And the YLabs platform is designed to do just that. In this example that we're seeing here, we have the brightness for several days of image data being logged, and for this particular metric, we could see in this distribution graph we have some basic descriptive stats, median, min, max, quantiles, and we have this thing called the distribution distance. We use Hellinger distance to calculate, to quantify drift by looking at the distributions of our incoming data in production and comparing them to the baseline that we define within the platform. We could see here that we had a spike in the distribution distance, which corresponded to a drop in the median brightness that we captured for each of the images in the data set. Looking at another example, we see a spike in hue, which this corresponds to the example we saw where it looked like the color channels were swapped. So this anomaly was captured as well. And in fact, I can jump back to a view of all the features that I'm gathering here, and we could see some correlations between the metadata that I'm logging and the metrics directly related to the images. I could see here the alert that's been generated for the anomaly detected in the hue corresponds to an alert here indicating that a different version of a library has been introduced. Or in this case, I see an alert for the image brightness, which corresponds to an anomaly in the shutter speed being used for these images. So thank you. I'm going to hand it back to Bernice.
Thank you, Ray. So I'm going to do just a very brief demo for natural language processing. So you can see another side of this. And for this, I'm going to use named entity recognition task. So what is named entity recognition? This picture, I think, summarizes very well what this task looks like. There's different ways you might configure this model. So for named entity recognition, often what I want to do is I have some text, like a paragraph or a document, and I want to tag, I want to basically select and classify named entities. So these are proper nouns, essentially. They're things like people or organizations or dates, that sort of thing. It's a difficult task in a lot of ways because it not only involves classifying a single token or word, there's often groups of words. So you can see less than a decade later, that together is a date. And it's a relative date, and things like names, so full names and organizations. Okay. So named entity recognition, again, can come in lots of flavors. We're going to see just one particular flavor here. And this looks to have several components, some of which are optional. So the input to the model is raw data. So this is the full text that's sent to our model. I'm assuming we're getting full text. Along with metadata that you may have with the application, as I've mentioned earlier. An optional step, but a common one that we won't see today in our demo is embeddings. So for some models, you will take this raw data and you will calculate or have look up your pre-calculated text embeddings for each token or word. And you would want to monitor those as well, right? So your embeddings, seeing your embeddings and whether or not they fit the distribution that you expect, have the properties that you expect, is really important component of this. Another component of named entity recognition that's quite common is parts of speech detection. So this is for every word or token. I want to detect things like, is this a noun? Is this a verb? Is this a past participle? I don't know any more of these because I am not a great NLP person or English speaker, perhaps. But this is also something that you'll want to monitor. And then finally, you'll see here your named entities themselves. So this is categorical data. Often, again, it's things like organization or person. It's a tag. So not the actual organization, but just the tag organization or person. And this serves as the primary output for a model. So we certainly want to capture this as well. Okay, so I'm going to jump into just a quick demo of this. Just for time purposes, I'll just kind of go over the highlights and then show what this would look like in the platform here. And I will say that this is not the best model that you could have written. That is not my goal here, just to demonstrate this. But I'm using NLTK, which is a great package for natural language. And so we have things like defining our simple parts of speech model. Luckily, the Natural Language Toolkit, NLTK library does this for me really easily. So I'm just taking the words and tokenizing them. So taking the data set and pulling out the raw data, tokenizing those words, grabbing the parts of speech tag, and doing a little bit of work to get the actual named entities using their any chunk tool or method. And so for the output for a document, so when I get that raw data, I'm going to store a couple of things. So the raw data comes with a file ID. It comes with a category. So this is the router's news data set. So there's kind of news categories. And it has a token count. So this is effectively the number of words And you can see it was a list for here, so I can just take the length of this. And this is the output of my very simple parts of speech model. I'm going to do some transformation of this data. This is largely just to make this simpler so you can see how a model might work, and to structure the output in a way that we might find pleasing. So I'm just going to take the outputs and kind of rename things into phrases, entity type, the start index, and so on and so forth, and put them in a pandas data frame. So you don't have to use a pandas data frame to use ylogs, although it is a very popular way of adding data. You can also pass this in a dictionary, in a Kafka stream if you want. Lots of different ways to pass in data. And then finally, I'm going to simulate some model error. The reason that I did this is I chose a data set that doesn't have labels. And so I'm just kind of making up some fake numbers you'll see here so that we can see how the performance metrics would work. Okay, so just to show you very quickly what an example model input and output looks like. So this is the model input, the raw text that we see here. This is a short article, I believe, or maybe even just a paragraph from an article. And this is an example of the model output. And so the reason that I wanted to show this, in addition to Ray's more in-depth image example, is to one, see some NLP, but then also to kind of demonstrate what happens when you have these complex models with intermediate steps. So in this output, you'll see multiple things. You'll see what is kind of like the high level output of the token count for the text, category, file ID, just the file that we got this from. You'll see the next intermediate step, which is this parts of speech. So for every word or token inside of our article, you'll see a different parts of speech tag. And then finally, at the bottom, you'll see the output of our actual named entity recognition model. So this is also a list of tuples with the named entities and the entity type. So organization, person, and then also the indices of the text. So I might want to know, where does this, so for example, China is the first word of our article. So this is why it starts with 0 and ends with non-inclusive 1. Okay, so I ran my transform output just to show you it in a prettier format, in the pandas format here. So now this is structured in a way that maybe looks a little nicer. And then I'll simulate my error. And then I'm going to create a data set attached to the dates. This is a slightly earlier time. And log this data to ylogs. I won't go in depth into how to log this, both for time and because this was created before our V1 launch. So our API may look a little bit different, but this example will be around in case you want to see the V0 version of this. Okay, so once we log this data, so using our logger.log, and our logger will go away and it'll be even easier. It'll be y.log to log this data in V1. And logging our, so our document level data, our parts of speech level data, and our named entity level data, as well as the performance metrics. Once I've done that, I can see what this looks like. So let's make this, oh, well, I can't do that. So I guess, so I'm inside of the YLabs platform here. And what I see is a number of projects. So there's different ways to set this up. I've set this up in 3 separate projects, maybe just to make it a bit more exciting and keep these as separate models. You can also formulate this in different ways if you wanted to put this in the same project under the same model right now, or other ways of configuring it. But what you'll see is a different kind of setup and some really great ways to detect issues in that data that we found. And this is true data. I didn't even add anomalies. So it's really nice to see that we're finding some of the issues with the data and how it's formulated. So for example, if I split this out by date, so I did kind of arbitrarily split them by date, I start to see some anomalies here for the number of tokens for some certain dates. And then if I look into the parts of speech, I see others. And then finally, if I look into the named entities, I see others. And then finally, there's performance. So this is our simulated performance here for this particular model, which isn't great, but I don't know why I simulated it that way. So that's all I'll say for our NLP demo.
All right, thanks, Bernice. That was a really great demonstration, even if it was cut a little bit short, about all of the features that we can have for unstructured data, including NLP. And similarly, thank you, Ray, for your demo of the computer vision and the image example. So I'm just going to spend a couple of minutes highlighting the things that the three of us have talked about and let you guys know about some next steps that you might have from here. So what you've heard here today is a really simple demonstration of just some of the features available in the YLabs AI Observatory, which is the SaaS platform that we offer that you can use for free today by just going to ylabs.ai/free. If you want to see any of those features for yourself, any of those performance metrics that Bernice was looking at, any of that input data metrics, any of those visualizations, or the alerts, monitoring, and triggers, and all of those other features that we didn't even get a chance to dive into, you can try all of them out for yourself for free without having to enter your credit card, without needing any of your own proprietary data, really as frictionless an experience as possible by just going to ylabs.ai/free and trying it out for yourself. But if you're not interested in trying it for yourself, also feel free to reach out to me. My email is danny@ylabs.ai, or you can also reach out to me on Twitter or on LinkedIn. My handle is up there as well. I'm happy to answer any questions that you may have about YLabs, about YLogs, about ML monitoring, observability, structured data, unstructured data, or anything else in the MLOps space. I'm excited to hear from you, and thank you so much for taking the time to listen to our presentation.